Good morning, everyone, and welcome back to our series looking at Australian pavement design. And in week 3, we'll look at asphalt and cement materials characterisation. So I'm Geoff Jameson, and there are my contact details once again. Today, we'll run for about an hour once again, including questions that you might have. And just remember to click on the Q&A button, type in the slide number and the question and send them through to me. That'd be great. So the discussion again today will be centred around the Austroads Guide to Pavement Technology and particularly part 2, which is the pavement structural design methods. But also we'll be covering material that's addressed in part 4B, which covers asphalt, particularly the mixed designs of asphalt, and part 4D, which covers cemented materials that we'll be discussing. So as well as part 2, you might want to have a close look at part 4B and 4D. So yes, today it's asphalt and cemented materials, and the presentation I'll first go through in terms of cemented materials, the definition of cemented materials and the types of materials that are used, the distress types, how we calculate a design modulus for use in our mechanistic empirical design process, and then how we estimate the allowable traffic loading of a pavement. Similarly for asphalt, I'll be going through the types of asphalt that are in use, the stress types that we design for, processes we use to calculate the design moduli, and again, the process to calculate the allowable traffic loading for an asphalt layer. So first turning to cemented materials. So our definition is it's a combination of a cementitious binder like cement plus granular material plus water that's mixed together and compacted and cured to form a bound material with tensile strength. So that's where we differ from unbound granular materials that we talked about last week. A bound material is a material that has tensile strength. So shown on that photograph there is a test site that where we've been doing accelerated loading, looking at the performance of cemented materials, and after that accelerated loading, we cut some beams from the pavement and did some testing for modulus and fatigue that we'll talk about later. But you can see how the material forms a block. It's bound together. So in terms of distress modes, the one that we designed for is fatigue cracking. And on the left-hand side of a photograph, there is that shows an example of block cracking that you might have for a very thick layer of cemented material. So initially, you might have some transverse shrinkage cracking. Eventually, that might then lead to a longitudinal load-induced crack, and then that leads subsequently to these blocks, like shown in this photograph here. On the right-hand slide is a cross-section through one of our accelerated loading experiments, where we didn't see cracking on the surface, but we did observe when we cut the pavement after the experiment, you could see where there was cracks developing at the bottom of the layer. So that gives you some idea of the cracking that we observe with cemented materials and what we design for. So in our mechanistic empirical design method, it includes a linear elastic model that we've talked about previously. Now, to calculate strains in that model and then relate those strains to performance, we need an elastic modulus, And we need to know whether the modulus is the same in the vertical and horizontal planes. And in this case, we assume that it is an isotropic material, unlike what we were talking about last week, granular materials, which are cross anisotropic. For cemented materials, we assume they are isotropic. We routinely use a Poisson's ratio of 0.2, and we utilize a fatigue relationship to estimate the allowable loading of the pavement from the calculated strain that we have in the mechanistic model. In terms of the processes that we have for calculating the design modulus, it is an estimate of the in situ flexural modulus after curing for 90 days in the roadbed. So it is a modulus at one point in time. You can see the modulus of cemented materials change with time. We've decided to adopt one point in time as our definition of design modulus, rather than a more complex characterisation that might consider how the modulus changes with time. These are some of the factors that affect modulus of cemented materials, and density is a critical factor, and the higher the density, the higher the modulus. So that's a very important factor to consider in coming up with your design modulus, what values you specify for density. Also increasing the binder content increases the modulus. We know that the modulus increases with age, but we don't allow for that modulus increase with age, as I've mentioned previously. It's just one point in time. And we assume these materials don't change with, the modulus doesn't change with temperature or with rate of loading, unlike what we'll talk later about asphalt, which we do recognise the rate of how the modulus varies with the temperature and the loading rate. For these materials, we don't allow for that. And also the other aspect is, in terms of their stress dependency, we make the assumption that the modulus of these materials doesn't vary with the applied stress level. So coming back to the methods that we use to determine the design modulus, there are three processes that we provide. The first one is laboratory flexural beam tests. We also use, we have a method to estimate the modulus from the Unconfined Compressive Strength, UCS. And then we have some presumptive values in the guide. If you don't have any test results on your particular material, there are some values to presume for different qualities of materials. So firstly, in terms of the laboratory flexural beam test, in recent years we've developed a test method for it, but it's still not commonly used in the characterisation of cemented materials. So this is some shots here of some of the photographs that we have from research projects that we've undertaken, where we've measured the 90-day flexural modulus of laboratory manufactured beams. So firstly, on the left-hand side there, we would compact the loose material in a mould with a segmental roller to the required density. We would then cure those materials for the 90 days, moist curing. And then we would put them in our test rig and measure the modulus. And there's a test method, as I mentioned, that's been developed recently for doing that test. Now, one of the issues is our definition of modulus is an in situ flexural modulus, not a lab a modulus that you obtain from the laboratory testing. And we've done that because we've found significant differences and variability in the in situ. When we've taken beams from the roadbed and tested them, we've found much lower and more variable results that we get from beams cut from the pavement compared with lab beams. things like shrinkage cracking are affecting the in situ values that are not affecting the lab values, where we cure them very well in a controlled way in the laboratory. So shown there is you know, some beams that we've cut from the pavement. You can see another one of our test pavements, and when we test those, some of the results that we've got are shown in that table there. The lab values are much higher and much more consistent than the field values. And that's been reinforced by other data we have, which is this shown here is one of our test pavements, a 100-metre long section, where we've back calculated the modulus of the cemented material at various chainages, and we've also taken beams for testing, and you can see the high variability in the modulus values along this project. And so we need to allow for that high variability in situ in coming up with our design modulus value. And the reason why we need to allow for that is it's the low modulus areas that crack first. And so so we need to consider that in coming up with our modulus value, and the design modulus needs to reflect those low modulus areas, because they limit the pavement life. So what we've developed based on the research that we've done is that the design modulus is 1/3 of the laboratory modulus after 90 days moist curing at the in-service dry density. And so that value of 1/3 was developed by research that we've done under accelerator loading and a program of laboratory testing. And that's the report that, if you want further details of how that factor was developed, I refer you to that framework report shown on the slide here. So a more common means of coming up with the design modulus for cemented materials is to use the unconfined compressive strength, or UCS test. That test is more widely available to road agencies than the Flexural modulus test. So, and UCS is commonly specified by road agencies. So it's a commonly used test. But there is uncertainty in predicting the Flexural modulus from the UCS. Of course, UCS is a measure of the strength of the material and in compression, whereas what we actually need is a modulus and in flexure. So they are different properties, and there's not a one-to-one correspondence between them. So there is uncertainty in predicting the Flexural modulus from UCS, but it is a common method that's used. And this is the form of equation that we have in the Austroads guide, where there's a simple factor of around about 1,000, 1,500 in that region here to estimate the Flexural modulus from the unconfined compressive strength. The third means of obtaining a design modulus is to use presumptive values. And in the guide, there are presumptive values there. For example, for a high quality base course material with 4 or 5% cement, you might use a modulus of 5,000, whereas for a sub-base material with 4 or 5% cement, you might use 3,000 MPa. So that is also a common means of characterising the design modulus of cemented materials, just to use presumptive values. Now, where cemented materials are used in pavements, there's often, or can be, depending on the pavement configuration, some useful life after the cemented material has fatigue cracked. And so in our mechanistic calculations, we allow for that life, the post-cracking life of the material. So this might be a situation, say, where you have 200 millimeters of asphalt overlying a cement treated material that's used as a subbase. If that cemented material cracks, there's still some usable life left in that pavement as far as the road user is concerned. It still performs okay. That cracking wouldn't come through to the surface, and there's some usable life left after that. So we need a means of characterising the design modulus in that post-cracking phase. And shown here is the characterisation we use. We basically assume that the vertical modulus is 500 MPa, that it is cross-anisotropic like a granular material. We don't sublayer it, as we talked about last week for granular materials, and commonly use a Poisson ratio the same as we use for granular materials. And that sort of information about the design modulus in the crack state was developed from results like shown in the graph here from some of the accelerator loading testing that we've done, where you can see on the vertical axis is the modulus of the material that we back calculated along test pavements sections, and on the horizontal axis is the number of loading cycles to surface cracking, just the beginnings of surface cracking. And you can see initially it might have started at a modulus of 10,000 MPa prior to loading, and then by the time it gets to a modulus, a cycles ratio of 1, the modulus is reduced to about 500 here. So by the time that we start to see surface cracking, the modulus has reduced to about 500. So next we'll talk about, well, how do we estimate the allowable loading in terms of fatigue of cemented materials? So we have in our mechanistic model an ability to predict strains, and in the case of cemented materials, it's a tensile strain at the bottom of the cemented materials layer, because that's where the cracking starts, as I showed in an earlier slide. But we need a means of translating those predicted strains to the time, the terminal condition of the pavement, when it would need to be rehabilitated because it's the surface is cracked. And that process is translating the strains to allowable loadings, requires a performance relationship, a fatigue relationship for cemented materials. So this is the general form of the fatigue relationship we use, where the allowable loading in terms of fatigue, or the fatigue life, is inversely proportional to the strain to the 12th power. So it's highly sensitive to the strain level, much more so than asphalt, as we'll see. And it behaves in a more strain intolerant way than asphalt, and more closely related to the strain or stress sensitivities of concrete. And you can see in that relationship also that we have a concept of a reliability factor, RF, that we'll talk about later. In fact, this is the slide here where I'll be talking about reliability factor. And so as we've mentioned in previous weeks, we have in our design process an allowance for the variability in performance between projects. Not all projects will perform the same. And so we need to allow for that variability in our predictions of how long pavements will last. And we do that through the inclusion of reliability factors. And you can see in this graph here, the significant effect the reliability factor can have on the predicted life for a given strain. So if we were designing for 50% reliability, as opposed to 95%, it would last 25 times as long. That's what we predict. So it has the choice of your reliability level for the project has a significant effect on the life that you calculate. So in terms of developing a fatigue relationship for cement and materials, there's a process that we have of testing beams in the laboratory to determine a laboratory fatigue relationship. And from that, you can calculate an in-service fatigue relationship. So shown here is some results of the laboratory testing. And from that, we'll determine an in situ fatigue relationship for use in design. And what we need to allow for in making that transition from a lab fatigue relationship to one for use in service is a laboratory to field shift factor. And that allows for the differences between lab and field. And you can see here, we've developed a presumptive value of that shift factor based on research that we've done with under accelerated loading, where we've compared the results of a laboratory test results, the fatigue relationship we get in the lab versus the number of cycles to a terminal condition that we see under a rolling wheel in situ. And essentially what we do is to increase the K factor in the fatigue relationship by a factor of 1.55. So you can see for a given strain, the in-service fatigue life is about a factor of 100 greater than it is from the lab than you'd measure in the lab for the same strain. So a big difference in how you translate strains to allowable loading in the lab versus the field. Now, if you don't have an ability to actually measure the lab fatigue lives, there's a process that we have in the guide that you can estimate what the fatigue, what this K factor is to use in your fatigue relationship from the measured flexural strength and the flexural modulus. And shown on the right-hand side here is some typical flexural strength values that we have for cement and materials. And, you know, for the sorts of materials that are in use commonly by road agencies, the flexural strength would be between 1 and 2 MPa at 90 days. So if you don't have an ability to do fatigue testing, but you have an ability to compact and prepare specimens for strength and modulus testing, there's a process here to calculate the K factor, a fatigue constant, for use in a presumptive form of a fatigue relationship. So if you'd like further details of that, the development of those processes, these are the reports that I refer you to. It's basically come from about 10 years of research that ARRB has done on behalf of Austroads from about 2008 to 2016, thereabouts. Just remember, please, to click on the Q&A button and type in the slide number and questions if you have any. So the second part of this webinar will talk about asphalt. Now, we discussed some of the definitions of asphalt in our first week, but I'll just go through again. Asphalt is, you know, a combination of bituminous binder with different size fractions of aggregate sizes, which are mixed, spread and compacted while hot to form a pavement layer. And so we have different types of asphalt, such as dense graded asphalt, open graded asphalt, which is commonly used as a surfacing type, and another surfacing type that's used as stone mastic asphalt. In week one, we also saw how asphalt is made in an asphalt plant, where we combine the binder, bitumen of various classes, some with polymers, some without, and different sizes of aggregates mixed together, then loaded into trucks, and then finds its way to the paver, shown on the right-hand side here. And then that material is spread by the paver and then compacted by rollers. So there are various sizes of mixers that are used, ranging in, say, a 5mm maximum size mix, which may be used, for example, for a footpath, to commonly 20mm would be a common maximum size mix that is used in Australia at the moment. And so the uses vary according to whether it's a wearing course. So for a wearing course, it might be commonly 10 or size 14mm. A finer, the maximum aggregate size is lower than what is used for base course. A size 20mm mix would be a more common size for base course materials. And the maximum size influences the thickness of layer that can be placed. So there's some rules of thumb there about the suitable layer thicknesses for use with different size mixers. So in terms of the load-induced stress types that we consider in our design model, we consider fatigue cracking, and that influences the thicknesses that we use in our design. In terms of asphalt, which in terms of rutting, which is the other mode of distress of asphalt layers, that is not addressed in our design model, but through the appropriate mix design and selecting material based on its mix design characteristics, the volumetrics, possibly wheel tracker testing of the material, and as the required qualities is specified by road agencies in their specifications. So for an intersection, for example, they might have experience that they need a mix of a certain type with a certain volumetrics compared with a freeway, for example. So there are the process of allowing for rutting of asphalt. We don't have a process in the structural design method, but it's covered elsewhere in terms of mixed design processes and in selecting and specifying the qualities of materials based on empirical knowledge about what is required for different situations. Again, in terms of our linear elastic model, which is part of our mechanistic empirical design method, we need the elastic modulus. For this material, like the cement materials, we assume that it's isotropic with the vertical modulus equal to the horizontal modulus. Presumptive Poisson's ratio of 0.4 is used, and of course we need to then translate those critical strains that we calculate to the allowable loading in service, and that's done through the use of a fatigue relationship. So in our linear elastic model there, you can see it's the tensile strain at the bottom of the asphalt that is used to predict the allowable loading. In the same way as it was for cemented materials, it's a tensile strain at the bottom of the layer. These are some of the factors affecting the modulus of asphalt, and critical factors here that are different from what we talked about for cemented materials is that we allow for the fact that as the temperature increases, the modulus decreases, and as the speed of loading increases, the modulus increases as well. So the faster the traffic, the higher the modulus you would use in design, and you'd use a different modulus, say in Queensland, than you would in Melbourne because of the temperature differences. So again, for this material, we assume that the modulus doesn't vary with stress level. It's no allowance is made for that in the design modulus, but importantly, again, the higher the density that you achieve, that it's compacted to in the field, the higher the modulus value. So an allowance need to be made when you derive your design modulus for the density that you're going to compact that material to in situ. In terms of our definition of design modulus, it's an estimate of the flexural modulus of laboratory manufactured beams tested at the in-service temperature and loading rates. So it's an early life modulus. Although we have data that available that shows that modulus increases with time, if it's sufficiently sound the pavement, it would increase with time. And in fact, maybe even double every 10 years. In the Austroads design system, we design for the modulus at one point in time, and that's the initial modulus value. We don't have a design process that allows for the variation of either the modulus with time or whether or not the material becomes more brittle with time. Those refinements haven't been made yet to the Austroads design system. So in terms of determining design modulus, up until recently, the indirect tensile test was used to determine the modulus of asphalt cylinders. But over the last 5 years, there's been considerable work done to improve the method of determining a flexural modulus of beams. And there's now an improved test method available to enable you to test for flexural modulus. And so there's more emphasis these days on using flexural modulus rather than indirect tensile modulus values. So the changes that we made into the test in recent years was to switch from haversine loading to sinusoidal loading. We had problems with the beam sagging when you applied a haversine load. A haversine load applies loading in one direction only. And so when we did that, when we used that mode of loading for asphalt, we ended up getting sagging of the beam, gradually displaced over time. And there was complications in terms of assessing what the state of the asphalt was, what the strains that were being applied in the test were. So we've now shifted to sinusoidal loading to overcome the beam sag issue. And when this test is undertaken on lab manufactured beams, we test over a range of temperatures and a range of loading rates, because as we mentioned earlier, the modulus of asphalt varies with both temperature and rate of loading. The higher the temperature, the lower the modulus, and the higher rate of loading, the higher the temperature, the lower the modulus, and the higher the loading rate, the higher the modulus. So shown on the graph there is some modulus values that were measured at 4 temperatures here of 0, 10, 20 degrees, 30 degrees, and you can see the values at 0 are a lot greater than the values at 30 degrees, as we would expect. And the values also increase with frequency. The higher the frequency of loading, the higher the modulus. And to utilise those results for any temperature and for any rate of loading, there's a process available where you can interpolate the modulus from what's called a master curve, which is the form of the relationship, which takes the form of the relationship shown on the slide here. So from those results, the results are converted to a reduced frequency, and this relation, and then you can interpolate the modulus at any temperature or any rate of loading within that temperature range. One of the limitations of this test is that we can't test above 30 degrees C, which is a major limitation for Australia, because a lot of our design situations have temperatures above 30 degrees. So in determining a design modulus from those results, you need to consider what your in-service temperature would be for your project and also your rate of loading. So you can see here that as the temperature increases, the modulus reduces, and also the higher the traffic speed, the higher the modulus. So we need to, coming up with a design modulus, you need to determine the modulus at the appropriate in-service temperature and rate of loading. Now, in terms of allowing for loading rate, we have a simple relationship shown on the right-hand side here to estimate the frequency of the test, the sinusoidal test associated with a heavy vehicle design speed. For example, if the heavy vehicle design speed is about 60 kilometres an hour, the frequency at which you should do the laboratory test is about 10 hertz. So we have a simple process to relate a design speed for the heavy vehicles for your particular situation to select what frequency to base your design modulus on. So this is a simplified procedure that's been developed based on the loading rate at a depth of 100 millimetres below the surface. So a single value or a single depth below the surface for all asphalt layers, regardless of where the depth of an asphalt layer below the surface. So in terms of temperature, of course it varies, temperatures vary between locations, say Melbourne or Brisbane or other cities, and also the temperatures vary from month to month and also hourly and also with depth. So it's quite a complex situation. Now, ARRB's done some work where we've measured temperatures in pavements and developed methods to predict temperature variations with depth and with time. And from that, you can see in that slide there, you can actually develop a process where you look at the fatigue damage for each hour of the year and sum those to come up with the overall damage. So models like that have been prepared. And this one here is for a motorway in Brisbane, for example. But what tends to be used is a simplified approach based on the weighted mean annual pavement temperature. And that approach has been used for 30 years in Australia. So it's a single temperature for each city. So for Melbourne, 24 degrees, whereas for Brisbane, it's 32 degrees. So it's a simple method that has been used, like the simple method we have for loading rate of just from the vehicle speed. The speed of loading is that at 100 millimetres depth for rate of loading, and we use a simple method for calculating the weighted mean annual pavement temperature rather than looking at the damage for each hour of each year. So we've continued to use that simplified method because when we've done comparisons between the simplified method of using the WAMPT and the simplified loading rate where V equals 2 pi F, the damage calculations are fairly similar to more complex characterizations. So at this stage, we don't see any reason to go to a more rigorous method of calculating the damage. This slide here just gives you an example of some of the design moduli that are being used. And in this case, it's the values for Melbourne that Vic Roads would specify. And you can see, depending on the size of the mix and also the binder class, whether it's a softer class 170 bitumen or a stiffer class 320, or a polymer like that A10E, the modulus changes and various values that you might use in design. Shown on this table also is the mixed volumetrics, and that's important to know as well, because the volume of binder there, that VB column there, is very important as far as the fatigue of the asphalt mix is concerned. So that just gives you some example of the variation of design moduli with different mix sizes that are commonly used in design. So then now I will turn to how do we predict performance in terms of asphalt fatigue in our design system. So again, we need a means of translating predicted tensile strains at the bottom of the asphalt layer to a terminal condition of fatigue in service. And again, that requires a performance relationship. Now in the Austroads guide, we have a presumptive in-service performance relationship. And that's a relationship of the similar form that's been used for a long time now. So it takes the form of as shown here on this equation shown on the slide here, where the fatigue life or the allowable loadings to that terminal condition depends on the applied strain, this tensile strain at the bottom of the asphalt modulus, the volume of binder, VB. As you increase the volume of binder, the fatigue life increases. We've also included a shift factor, a lab to field shift factor, as we talked about earlier for cement materials. And of course, we include reliability factors as well, the same as we do for, I've explained earlier for cement materials. So this is a presumptive in-service fatigue relationship. And the origins of that was based on laboratory testing done by Shell in Europe more than 35 years ago. So that forms the basis of the current presumptive means of predicting the fatigue life of asphalt mixes in Australia, based on European mixes a long time ago now. So as part of that process, includes a shift factor to relate the mean life in the lab by this Shell fatigue relationship, and a lab fatigue relationship, to a mean in situ or in service fatigue life. And that shift factor takes account of things like vehicle wander across the wheel path, intermittent loading of the pavement, and there might be, say, some healing of damage between load pulses. And also, importantly, differences between predicted strains through our design model and actual strains. So the value of the shift factor only relates to the Austroads design system and the way we predict strains. It relates the way we predict strains to the allowable loading in service. So if you had a different model of predicting strains in your pavement, the shift factor would be different. So this has been tailored to our method of predicting strains, because predicted strains can differ from actual strains. So in terms of how that shift factor of 6 was derived, we did Monte Carlo simulations almost 20 years ago now, looking at the distribution of as constructed pavements because of variations in layer thicknesses, layer moduli, volume of binder, for example. We allowed for all those variations that you might get in constructed pavements. And you can see we simulated the distribution of possible lives of projects. And when we put that distribution to our panel of experienced road agency designers, their view was that if we just use the Shell fatigue relationship without a shift factor, in other words, a shift factor of 1, 95% of constructed pavements would outlast the design traffic. So they thought that if you just use the design system with a lab fatigue model, that the designs would be highly reliable. And so the view was that 95% of pavements would outlast the design traffic. And based on our simulations, that resulted in being a factor of 6 between the mean life and the mean in service life and the mean lab shell lab life. So that's where our shift factor of 6 came. It came from the simulation of the variability and a judgment that when you use a shift factor of 1, or in other words, just the lab fatigue model, that the designs were highly reliable in terms of predicting the performance. And then we've also included from that simulation work reliability factors in the same way as I explained for cemented materials. Now, an alternative means of obtaining a fatigue relationship is from laboratory fatigue testing. And as I mentioned earlier, there's been considerable work in recent years in refining the test method, and shown here is the test method that's been developed in the last 5 years, where we would commonly test a minimum of 18 test beams at a certain temperature. Normally it would be a temperature of 20 degrees and a loading rate of 10 hertz. Now, one of the limitations again with this is that the maximum temperature that you can use for this test is 30 degrees. And there are situations like in Brisbane, as we saw earlier, where we'd use a weighted mean average pavement temperature of 32, where we can't actually test, do a laboratory fatigue test at that temperature. So that is again a major limitation of the methods that we have available to us. So if we did measure the lab fatigue life, one of the challenges is that we then need a shift factor that relates a lab test result to the mean in service life. So I talked about earlier, there's a shift factor of 6 between that shell model of estimating the laboratory fatigue life and the in-service life. In the case where we actually measure the fatigue properties of asphalt mixes in Australia today, that shift factor of 6 doesn't necessarily apply. And so we need to come up with an appropriate shift factor between measured values rather than using a presumptive fatigue relationship. So that research is yet to be done, and basically we need to test in Australia a wide range of mixes using that new test method and determine an Australian laboratory fatigue relationship. And from that, we'll be able to come up with a shift factor. And basically what we're saying is that we think that work is really a high priority for us to improve on this shell model that was developed over 35 years ago based on European mixes. We need to update it with current Australian mixes and using current Australian testing procedures. Another area of research that is needed is how we allow for variations in the shift factor between lab and field with temperature. There's a view around that basically we're not allowing for the healing that can occur to fatigue damage at higher temperatures. And you can see on this slide here on the left-hand graph is how the required asphalt thickness increases dramatically as the temperature increases with the current design process. For example, at 42 degrees, you might, for a design traffic loading of 10 to the 8, you might need a temperature of about, a thickness of about 380 millimeters. Whereas at a temperature of 24 degrees here in Melbourne, the required thickness is about 100 millimeters less. So a dramatic difference with temperature. And the bit that we question is whether or not we've allowed for the increase in healing that can occur, healing of fatigue damage with temperature. And shown on the right-hand side is an alternative model that we've been looking at, is where we actually trying to vary the shift factor with temperature to better reflect what we think is happening in terms of healing of damage, the increase in the damage healing with temperature. So that work we think is needed to improve our design processes and really address the issue of possible over-design of thick asphalt pavements at high temperatures. So if you'd like some more information about those issues, about how the current processes were derived, and also this issue of fatigue damage healing and the concept of fatigue endurance limits, I refer you to these reports here. So please remember, if you've got any questions, click on the Q&A button, type in the slide number and your question. So I'll now hand it back to run through some of the questions that might have been submitted today.
Thank you, Jeff, for the great presentation. We have a couple of questions from the attendees. Yeah, the first question is on slide number 30. Yep. Was the block cracking distress in the photo for a pavement with a thin asphalt surface overlaying a cement-treated base?
Sorry, can you run through it again, please?
Yeah, sure. Was the block cracking distress in the photo for a pavement with a thin asphalt surface overlaying a cement-treated base?
I'm not quite sure what the question is. I can't quite understand it, but basically that photograph there looks like it's a thin asphalt surface, or it could be a sprayed seal surface on a cement treated base pavement. So in terms of the size of the cracking there, we don't have any firm data, but my belief is that the stronger the cemented layer and the thicker it is, the bigger the blocks. So if you have thinner layers and less strong materials, you'll get smaller blocks develop with time. So the nature of that cracking is of interest to us. We're currently trying to develop some new processes for lightly cemented materials. So these are materials that might have 1 or 2% cement rather than 3, 4 or 5% cement. And they have reported to have different cracking characteristics than for cemented materials. And so we're trying to allow for that in these new design procedures that we're developing, how we induce finer cracking rather than macro cracking in such materials, which we call now lightly cemented materials.
Thanks, Jeff. That clarifies the question. And next question is on slide number 24. Can you please explain why cementitious material modulus reduces as load cycle increases?
Well, it's if we see any bound material, and we've done this sort of testing both in the lab and in service, asphalt, cemented materials, or foam bitumen stabilized materials. As the damage accumulates, there's micro cracking in the material, in these bound materials happens due to loading. And that micro cracking results in a loss of bond between the binder and the aggregates. So you get micro cracking happening as a result of the energy induced by the loading. So it cracks bonds in the material. And because of that, the modulus reduces. You haven't got, you develop a micro cracked state, which eventually leads to macro cracking of the pavement. So you can see in this slide here, the modulus reduced significantly initially in the first 10% of the number of cycles to from when we first saw cracking. The modulus is more than halved just in that period. So there was quite a lot of effect of the initial loading in reducing the modulus of the material well before you could see any fatigue damage on the surface. And probably even if you cut trenches in those roads, you couldn't actually detect the cracking that was there. It's so fine, the micro-cracked state, that it wouldn't be detected by eye. But it has been damaged structurally, and so we allow for that change in the state of the material in our design processes.
Thanks for the clarification, Jeff. And the next question is, what are the technical difficulties that you would expect if the asphalt flexural beams are tested above 30 degrees in the laboratory?
Well, the issue when you test at high temperatures is basically see if I can go to the slide here that shows some of the testing. I'll go back to this one. When you have that sort of test set up there where you're measuring the modulus, at higher temperatures, you get deformation of the material. So the support clamps, for example, can actually press into the material at higher temperatures, and you actually get deformation of the material happening. So it's not behaving in an elastic manner at high temperatures. So that's the issue, that it's no longer an elastic material. And so there's just difficulties in actually estimating a valid fatigue life from the testing, and also a valid modulus value above 30 degrees.
Thank you, Jeff. And next question is, fatigue life of a subgrade material, which is black soil, stabilized with cement and additives to be examined. And they believe that this material behaves as a bound material. And what test method would you recommend for this evaluation, whether stabilized material approach or asphalt material testing approach?
Well, it's if I understand it correctly, there's a sort of situation where you might treat a clay subgrade with a lime, by lime stabilization might be, I think, what you're referring to.
That's cement with additives. It mentioned that.
Right.
Stabilized with cement with additives.
Yeah, it's either, if it's a subgrade material, a more common treatment would be lime, but
Lime.
just whatever it is, a cementitious binder is more commonly used in a bituminous binder. In that case, the closest we've got to that situation is our cementitious characterisation, what I described for cemented materials, where you could measure prepare lab beams if the binder content was sufficient to prepare a lab beam, and measure the lab characteristics, lab fatigue characteristics. How you would translate that to an allowable loading, what the shift factors are between lab and field has yet to be determined. So there's a whole research opportunity there for someone to develop a process. There's no processes we currently have to translate the fatigue of a stabilized subgrade layer to an allowable loading. And the question is, if after it does crack that layer, if you have a process there to predict the fatigue life of that layer. What is the consequences in terms of when you would rehabilitate that road? Does that cracking come through to the surface and therefore limit life in some way, or lead to additional rutting of the pavement subsequently? So there's also a question of how you would address how that influences the time at which a pavement would be required to be rehabilitated because it's distressed. So there's quite an area of research that could be developed along those lines.
Thank you, Jeff. And I have a question. The size effect. Has size effect taken into account for fatigue performance of cementitious materials? In the literature, it's shown that concrete materials heavily depends on the fatigue damage of the concrete materials heavily depends on the size tested in the laboratory, size of the beam tested in the laboratory. Higher the beam size, lower the fatigue life for a given stress level. And I was just wondering whether this has been taken into account when we design pavement thicknesses from 550 millimeter to 400 millimeter using the same fatigue equation.
As I explained, we have a process here that we've developed a shift factor between our current test that I described. There's a test method there that I described here. Not sure where it is now. We have a certain test method and a certain size beam. In our case, it's a 100 millimeter square beam, being about 400 millimeters long. So based on that research, we have developed a shift factor to translate the performance with our test, 100 millimeter square beams, to an in-service fatigue life. So that shift factor of 1.55 only relates to our test. If there was a different size beam, a different test method, then a different shift factor would apply. So yes, it does depend on the testing equipment. The values that we have been are appropriate for the tests we currently use. If there's another test around that's subsequently developed, then there'll need to be further work done on coming up with a shift factor that's appropriate for that test.
Thank you, Jeff. So that's the last question. And with that, I'll hand over the session to you to wind up.
Right, thank you. Well, thank you for joining us again today. Next week, we'll be covering the design traffic. And this is important in our thickness design processes because we're designing for load-induced damage. And we need to characterize the truck loads that are on our pavement and how much damage they're causing. So that's what we'll be talking about next week, our design traffic, how we come up with the process of quantifying the damage due to the traffic on the roads. So thank you again for joining us and see you next week.